Would you like to improve optical wireless communication? Would you be interested in doing a PhD in this topic? Well, we have a position here at Eindhoven University of Technology. I'm Johan Lennarts.
And I'm Piyush Kaul.
Piyush, I'm looking forward to start working on that, on a topic which I like a lot, but maybe let's explain why optical wireless communication is interesting.
Yes.
Compared to radio.
Yeah. So yes, definitely. I'm looking forward to working on this topic as well. So typically what happens is that when you use wireless communication, the thing that comes to our mind is radio frequency signals. So using 5G, 4G, all these signals to communicate wirelessly. Now, what happens is that as the number of devices which use the spectrum keeps on increasing, then
they just interfere with each other.
Each other, exactly.
And that is a main limitation to performance these days.
Yes, because you want to achieve high data rates, you want to achieve the connections reliably, but you end up with limited spectrum.
I know a piece of spectrum that is for free.
Yes.
Light. So there are applications for that. We see a lot of research doing it outdoors to connect base stations again, but also in indoor communication.
Yeah.
Indoor. Is that important?
Yes, definitely. If we look at, let's say, the number of devices that communicate, outside is only part of the wireless communication domain. Most of the wireless communication happens indoor. So for indoor applications, it's quite important that we look into alternatives to radio frequency signals.
And that's where quite often we experience that Wi-Fi is bad, simply because there's so much interference, so much competition, too many users, too many Wi-Fi stations. With radio we can target a beam. That could also make it more secure. We see a lot of applications for security. But more and more industry 4.0, physical AI, places where devices need to communicate with images that are to be processed in AI at the edge or in the cloud, then communicating in an optical way with a beam is an interesting thing, is a very promising approach. So let's make it better.
Yes, definitely.
And now I see everyone working on improving lasers.
Yeah, so of course, in an optical wireless communication link, as is the case with an RF link as well, that you have a transmitter and a receiver. And then, of course, the focus could be on the transmitter, where you want to create the signal with enough power which can be sent to a receiver over a certain distance. And on the receiver side, you have a detector which has to detect the light and convert it into a form where it can be post-processed.
Can we take the detectors off the shelf?
I don't think so. So, yeah.
Because there is a challenge in improving the detectors, and I think there's a lot of attention on the emitter. The lasers go faster and faster, they can be modulated very rapidly. And the detector can also go very fast, provided that we make it small.
Well, yeah.
And there we see very fast detectors, but that's not something that is very useful indoors.
Yes.
I mean, I could build a big lens and then focus the light to a tiny spot. There's no turbulence indoors, so it's really a spot. And then we have very fast communication.
Yes.
So all the robot vacuum cleaners will have rotatable lenses on top of
it. And also your mobile phones, maybe.
That's not the vision that we have in our project.
Yes. So we would like to look into detectors which are more flat. So we would want detectors which have a very wide field of view so that you can capture the light, and also have a large aperture, but be flat. So there is no need to have big lenses attached to your devices.
So now I come in, okay, let's do a PhD at TU Eindhoven. I just make a big detector. Done.
So
there's an easy way to get a PhD, right?
Yeah, that's true. Well, yeah, if you...
Not exactly where the problem is, because the larger and larger you make your detector, other problems come in.
Yes. So, because the idea is that you want to make a large flat detector, but then the problem is that you end up increasing the parasitic capacitance associated with that detector. And because you have to connect electronics to interface the converted optical signal to a form which can be post-processed by your digital circuitry in your system. Now, when you attach this electronic component, which is a transimpedance amplifier, a TIA, to a detector, you end up losing your signal because of that large parasitic capacitance associated with your large detector.
Or what I also understood is that indeed the trans amplifier transimpedance amplifier tries to do its best to boost the signal, but then the noise goes up in that process because of the capacitance attached to it. But there are tricks.
Yes.
I even understand that there are cameras that also are large and are operating very well. So we could chop up the large photodiode and then build a transimpedance amplifier for every pixel, and then you are in business as an electronics engineer.
Yes.
But it may be a bit over the top.
Yes, that's true, because a transimpedance amplifier is still an amplifier. It consumes power. So from an energy efficiency point of view, maybe having a transimpedance amplifier for each pixel may not be the most optimal solution.
And pretty costly.
Yes, that's true, because like for a detector, especially when the detector scales over large array sizes, then having multiple TIAs is, of course, it's not cost efficient, it's not energy efficient, and it's quite complex to design, because TIA is not just a single input and a single output device. You have DC signals which have to be attached to
for all these amplifiers, you need a relatively large die area in a pretty costly process.
Yes.
So we may do something else.
So one idea would be to kind of look into different configurations of the photodiode array and the TIA together to see which one is the most optimum. So it's kind of like a system level study, a system architecture study, where you want to optimize the performance or the throughput of the system with both the detector and the TIA interfaced together.
Yeah, we have some ideas of playing with series and parallel photodiodes.
Yes. So one idea would be to kind of focus on the detector and see how we can reduce the impact of the capacitance on the electronics. And on the electronics, the focus could be how we can reduce the impact of noise on the system itself.
Can you give an example of reducing the capacitance?
Yes. So an example would be that if you have the large detector that you want to chop into individual pixels. Now these individual pixels can be connected in parallel. So what ends up happening is that you end up increasing the signal strength, because all the currents from each of these pixels add, and then that current goes into the TIA, which converts it into a voltage. However, you end up increasing the capacitance as well, because even if the individual pixel is small, it still has an associated parasitic capacitance.
Many in parallel is essentially the same as making one big one, electrically.
Yes, that's true.
Okay.
Yeah. So then the thought process comes, okay, how can we reduce this capacitance? So what you could do is, like if you have a 4x4 array, or let's say an 8x8 array of 64 pixels, you end up adding or kind of putting the 8 pixels in series in each row. So you have 8 columns, or kind of 8 rows, and 8 pixels in each row are connected in series. So you end up reducing the capacitance, because in series the capacitance reduce. Like when you add it in series, then it reduces. And then it only adds for the combination of this 8 series pixels.
So partly in parallel, partly in series.
So it helps in reducing the capacitance. But the other trade-off is that the current reduces as well, because now you are not adding currents from 64 parallel photodiodes, but only from 8 parallel photodiodes.
And you even putting current sources in series.
Yes.
Which is an interesting thought idea in circuit design. But if I look at this from a communication system perspective, which is more or less my field of view, then we learned from the Shannon expressions that improving bandwidth helps a lot in increasing the throughput, but increasing the signal to noise ratio or jeopardizing the signal to noise ratio does not have so much of an effect, because there's this logarithm in signal strength. Now, the situation here in optical wireless is different, so we have to think a bit further than these basic expressions. With a single capacitance, quite often you get a gentle first order low-pass filtering effect. So if I have a little bit more power, I could also spend that to electronically compensate for the bandwidth. So extend that by the different techniques that we have for that, and just push through by playing with the channel response. And then there we get that trade-off, but we could also think of things that go beyond this and improve the whole design by addressing pixel by pixel. and then not by having transimpedance amplifiers per pixel.
So, yeah. But having, let's say, a configuration of a certain number of TIAs which are different from the number of pixels.
Yeah.
And what that number is part of the exploration in this project.
And then the tricky thing is you need something in between. Electrically, you want to load the pixel element with a low impedance,
yeah.
because then you get rid of the capacitance effect.
Yes.
And to have a high impedance to really feed and push a current
yeah.
into the transimpedance
It's an amplifier, yes. So then that would be so that basically implies that a component or a device which can act as a buffer between the photodiode array and the TIA, which can help achieve this low impedance path and a high impedance path for the photodiode and the TIA respectively.
Where there are some ideas with cascode transistors.
Yes, so essentially having a common gate or a common base transistor in series or
Yeah.
in between the photodiode array and the TIA.
Yeah. We have a project to work on that. What I understand is that we need people who know and have seen how photonics works,
Yeah.
to see how photodiodes work, what their properties are. I also certainly believe that it's important to look into it from a communication system perspective, what modulation methods to use, but there's also, and that's your expertise,
Yeah.
a large electronics part.
Yes. So yes, because here it's not just about going from working on the system itself, but also kind of making demonstrators and making chips, which can actually help us test our hypotheses. So this project also involves designing TIAs or and integrating them with the photodiodes.
So we're looking for expertise in that direction. We can have nice high-level debates about it, but we really need to dive deeper to check it, and we have a PhD position for that. In fact, 2 PhD positions.
Yes.
And we're looking forward for a good candidate.
Yes. And are you that candidate?